Right, so in question 54, what we've got is we've got a steel beam, and that steel beam has some weight, and so in order to pick it up, there's two cables which are applying tension forces to it. So first of all, I shall represent the weight of this cable by a vector called W, and then the tension forces being supplied by the cables I shall draw as, let's call it T1, and there is a T2 as well because there's two cables. So we have this kind of situation, and those two cables are making an angle of 70 degrees. So that means we know that the force that these things are applying to the steel girder are at an angle 70 degrees to the girder. So I'm just going to call it theta. And what we're told about theta is that it's 70 degrees. Now the weight of this steel beam, which is another force acting on it, has magnitude of 8,000 newtons, and that's obviously going to be pointing straight down. And so we're told that this thing is being lifted at constant velocity, and it's asking us what is the tension, so what are the forces basically that these two cables are applying to this steel beam. Now when we have constant velocity, of course, we have no acceleration, which means that the net force acting on this thing is just going to be zero. So if we want to figure out what these tension forces are, a good place to start would just be to add these three vectors up and find out what the length of these two vectors has to be in order for the sum of those three to give us 0. So what I like to do in this situation is to split these vectors up into components and then add all the components in each of the two perpendicular directions up. Because I know that the net force is going to be 0, and so the x and y, say, components of the net force has to be 0 as well. So let's just define what I mean again by x and y. So here I have an x-axis and a y-axis. Let's now split these vectors up into the x and y components and then add those components up to find the x and y components of the net force, because we know that those x and y components of the net force have to be 0. And that'll give us a couple of equations that hopefully we can solve for what the question is asking us for, that is the tension in these two cables. So if we go split vectors into x and y components. So let's start with the weight. That looks pretty easy. So I would say that the x component of the weight is just going to have to be 0, because the weight is acting vertically down, which is in the y direction, so it has no x component. The y component of the weight is just going to have magnitude equal to the magnitude of the weight itself, which is 8,000 newtons. So that's going to be equal to W, with a little minus sign, because the weight is acting in the negative y direction. And now let's think about the x component of the tension force supplied by the first cable. Well, let's get ourselves a right-angled triangle around this vector here. And then we're going to have that this side length along here is going to have length equal to the length of the x component of this tension force. And this side here is going to have length equal to the length of the y component of this tension force. So if we knew what the magnitude of this tension force here was, we could calculate these x and y components quite easily. Now, of course, we don't know what that is. That's what the question is asking us for. But if we just give it a symbol, so obviously we've given this a symbol t1 vector, so the magnitude of this vector is just going to be t1. So we can't give it a number at this stage. That's what we're trying to solve for. But if we do that, if we just write down expressions for what the x component of this thing is, then hopefully that will lead us to an equation which we can solve for the length of this vector. So in that case, the length of this x component then is just going to be t1. So the length of this tension force, or sorry, the magnitude of this tension force, or equivalently the length of this hypotenuse, multiplied by the cos of this angle, because the length of t1x is just equal to the side length of, to this side length, which is the adjacent side of this right-angled triangle. But we do have to put a little minus sign there, of course, because t1 is pointing in the negative x direction. And now the y component of t1 is just going to be the same thing, except now we want the opposite side of this right-angled triangle, so we're going to have t1 sine theta. And since t1 is acting in the positive y direction, we just have a plus sign there. And the same type of thing happens for t2. If we get ourselves up another right-angled triangle around here, this side length here is going to be equal to the length, so to the magnitude of t2x, and this side length here is going to be equal to the magnitude of t2y. So this side length here is equal to the length of this adjacent side of the right-angled triangle, so we're going to have that's equal to t2 cos of theta, and t2y is equal to the magnitude of the second tension force multiplied by sine theta. And that will also have a positive sign because t2 is pointing in the positive y direction. So now, since steel beam moves at constant velocity, the net force F net on it has to be 0. Thus, so too, the x component of that net force and the y component of that net force. So if we just write down an expression for what this net force in the x direction is, that's got to be equal to 0. So F net, so the x component of F net is just going to be equal to the x component of the weight plus the x component of one tension force plus the x component of the other tension force, and that has to be equal to 0. And if we just substitute in these expressions, we find that that's going to be 0 minus t1 cos theta plus t2 times cos theta is all equal to 0. And here we see that both these terms here have a cos theta out the front on them. So we could just cancel cos thetas, so divide both sides of this equation by cos theta, and we'll then get that minus t1 plus t2 is equal to 0. And in that case, if we just add t1 to both sides, we find that whatever the tension force in this cable is, that has to be equal to whatever the tension force in this cable is as well. So let's just go, just to simplify the notation, we'll say let big T is equal to the tension in cable 1, which is equal to the tension in cable 2. So now let's add up forces in the y direction to find the net force. So if we repeat what we've just done in the y direction, we find that the net force in the y direction has got to be equal to the y component of the weight plus the y component of the first tension force plus the y component of the second tension force. And if we just plug these expressions in, we find that gives us minus W plus T sine theta. So here I've used the fact that T1 is just equal to what I've called T, and plus another one, so plus another T sine theta. And this has to be equal to 0. So we can clean this equation up a little bit. We have two lots of T sine theta, so we can group those together with a factor of 2 out the front. And that has to be equal to 0. And now if we just add W to both sides, we might get something useful out of it. So let's add W to both sides. And so we find that this is 2T sine theta equal to W. Aha! Now we know what this weight is, and we know what this angle is. And so the only thing we don't know is this tension, which is exactly what we're trying to figure out. So if we now just solve this equation for T by dividing both sides by 2 sine theta, what we find is that the tension force in each cable just has to be equal to the weight of the beam divided by 2 sine of theta. So let me stick that into the calculator. And what I get, since the weight is 8,000 newtons, divided by 2 times sine of 70. And that gives me a force which is approximately equal to 4,260 newtons.